So let's get started. We'll talk about some of the common mistakes and also how to improve the solutions of your assignments. So first, you should try to write readable solutions. For example, we see something, we see some, these are real solutions. This is from the midterm. So we have some trouble grading midterms that are not written in a linear fashion. Like for example, this one is something that with a very clear structure and also a linear order. But for this one, this is mainly a draft. So it will be very hard for us to grade this. So please try to write down your draft first, and then later when you are sure that your proof is fine, you turn your drafts into your solution. Because you should have enough time to do that if your idea is correct. And then there are some quite typical low-level issues that we found in some of your solutions. For example, some of you might be a bit lazy and use some of the less popular short forms. For example, this FTSOC. We are not very sure what this means. So yeah, and also this exists. Suppose there exists two, like this is not typical short form, and this, I guess this is a contradiction. Yet just try to write the full test. So for the sake of contrary, suppose that there exist two nodes, for example, and here you can just directly write there is a contradiction or something, like don't write abbreviations that are not commonly used. Also, try to check if things are defined earlier. For example, when we see this, the student used this S function, which presumably means size, but the student never defined this function S. So it may or may not be correct, because there are some students have misunderstanding for heavy light decomposition. So yeah, so try to make sure that everything you use is defined. And also there are some students having this kind of just presentation issue. And also for this example, they are saying something like we attribute to the sum of the two nodes, but this is not the typical way you talk about tree vertices. For example, for trees, we consider each node to have one parent, exactly one, and possibly multiple children. So say if we draw the tree like this one is the parent, and these are the children. And for this sum of the two nodes, I am not entirely sure, but I presume the student want to mean this, where this is the sun. But there can be like cases like this, and yeah, like try to use the typical notation. But this is the parent, and these are the children, and also you have things like ancestor, descendant. Like yeah, try to use the typical notations. So now we talk about the typical structure that we are expecting from your solution. So we expect you to have an overview of your algorithm. So which approach are you using? For example, dynamic programming, greedy algorithm, sweep line algorithm, etc. And also what data structure will you be using and for what purpose? So if you use a self-balancing binary tree or prefix tree or segment tree, please state that. Like at first you should say something like we will be doing a bottom-up dynamic programming, and we will be using, say, a tree or something like that. And we will be using a breadth-first search. So we expect some kind of an overview of how your algorithm is designed and how each part will work. If you don't give us an overview, it will become very hard to follow. For example, for this, you immediately tell us how would you pre-process the input, blah, 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 blah. But because we don't know the purpose of this, we have to extract your purpose from your description, which is very hard. And especially when there are like tiny cases that are wrong, like edge cases that are wrong, we may guess the wrong thing. So try to give an overview of your algorithm. And then in the algorithm description, try to state the purpose of different parts of the algorithm with some conventional notations. And also if you are using, you are writing some low-level details, just use pseudocode instead of natural language. The example here, here is an example. So this is a bad example. So for example, for this expression, we don't really know what is A and what is B and what do you mean by P prime AB? Because typically we are expecting A equal X plus Y, or better, you can just say let A equals X plus Y. Like you know that you are defining this A, but here it becomes quite unclear what you are trying to do here, because we don't know if this is equality or assignment and where this A comes from, and also what this P prime means. And also, when you define this P prime, you should try to state what do you want to do with this P prime. What is the purpose? The purpose is mainly for the homework to Manhattan distance thing. You have the grid you are searching is like this. You are rotating it into a grid like this, where this is the A-axis and this is the B-axis. So this is your purpose. You can just say that in the transform coordinates, we can direct it to the grid search or something like that. And then, yeah, like this is a better example. It says that finding the number of points, blah, 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 is equivalent to finding this and this. And also, yeah, more concisely, you can just say let A equals X plus Y, B equals X minus Y. So we know that you are defining a new variable A and a new variable B. And when you are describing your algorithm, try to split your description into the specification as well as the implementation of the algorithm. So the specification is about what you are computing, like the mathematical abstract thing that you are trying to find. And also you should state the invariants or properties when you are talking about the specification. So usually when we are talking about correctness, optimality, we are talking for your specification part. And when the and for the implementation, it is about how do you efficiently compute the abstract mathematical thing. So it would be slightly lower level for the implementation part. For example, for homework 1, exercise 2, you are trying to compute the winning set for Alex. So you can also think of it like an attractor set. An attractor set contains of A1, so A1, A2, etc. Up to AN. And where each AI is the vertices in which Alex can win in k steps. So this is the property, like this is why you define this AK. Like you want to say that what is the reason for you to define such a thing? And then you in the solution you may say, okay, you define a function that when given AK returns AK plus 1. And then this is the rule for computing that function f. And for question 1, you just run it for k iterations. For question 2, you run it until it reaches a fixed point. And this is already the algorithm, like this is already the description. And but for implementation, you may want to say that, okay, why you can do this in linear time, say O(n) plus n. You are using something very similar to BFS, say, and that is the implementation part. And note that you should try to explain why you want to do this. For example, for this question, why you want to add B to the attractor set, AK plus 1. Yeah, so you should explain why, and your explanation can serve as the correctness proof vector. So usually description contains some of the invariants, and they are usually parts of the proof. So you don't have to do something like you have the description, and then you don't have to explicitly have a section of proof of correctness. You don't really need a separate section of proof of correctness. Proof of correctness can go inside the description part. And for homework 2 exercise 1, you may want to use some sort of a sweep line algorithm, which means that if this is the x-axis and this is the y-axis, sweep along the x-axis means that you are considering points inside this region, like inside this red region, and you are moving this red part to the right, like to the positive x direction. And the invariant is that you only consider the points you consider, say they are inside a certain data structure, only have x inside this range. So this is the invariant you want to use, and you should say that. And then how to implement this, you can just sort by x coordinates and iterate over them. Yeah, so this is in general what we're expecting from the description. When you are writing the algorithm description, if it is low level, please just use pseudocode. Like for example, yeah, this is not a high level description. So please don't use natural language for this. This is hard. Yeah, this is pretty hard to read and follow. Because as for pseudocode, you can have things like indentation, and also the syntax is much more compact. You can read it quickly, but if you turn them into pseudocode, you have to read a lot more, and it can be a bit hard to understand. And also, please don't use errors like this. This is impossible to understand for some. So you want to write it like x equals y dot left, and t2 dot x equals right. Sorry. And And this part is x dot right equals y or something like that. Like you use dot for field access and don't use this C++ syntax for pointer field access, especially when you want to use the left arrow for assignment operators. And also when you are using subscripts, please try to make it mathematical and don't use this self-increment, because it can be, well, we understand that what you mean is y plus begin or something like this. Using subscripts like this is still quite hard to understand. Also, please use the same naming convention. Throwing this at me is hard to understand. Use something like camel case or underscore or whatever you like. Please chop it down. Okay, so anyone have questions about what we want about the solutions? I can elaborate on some of these, and I have more examples. Yeah, so I assume no. And now try to prove things even if they seem obvious, or at least try to make some examples and test them. Because for question 1.1 in the midterm exam, a lot of you assume something is trivial and go to the wrong direction. In a question that we thought is like free score for you guys. So this is not what you really want. So here we consider this question, a brigade city U can guard its own city as well as any city that is directly connected to you. Some of you say that the node with a brigade should not be adjacent to each other's, and this should be a two coloring. So the solution is just picking the color with the least number of vertices. But this is obviously false, because here the optimal placement is this, as well as this 2 and 5. But if you try to color this graph, to say you color this black, it induces this coloring. So this 2 and 5 must have different colors. So 2 coloring is simply wrong. Also, the intuition that these brigades should not be adjacent to each other is also wrong. Because for this example, you see that the optimal placement is here and here. And any other placement will require 3 vertices. So try to, even when you think something is trivial, especially in the exams, try to prove them, or at least give some non-trivial examples and try to run them, because many of the times things are not that trivial. And the actual solution for this question is a simple greedy algorithm. So you root the tree. So for example, for this graph, you turn it into something like this, where this is the root. And then you find all leaf nodes that are not being guarded. So this is not guarded, this is not guarded, this is not guarded. So you tag this one, and then you delete them. And then this is guarded by something previously, so you don't have to consider this, and then done. Like this greedy algorithm works, and here's the proof sketch. So usually for this kind of optimal solution problem, you want to prove both validity of your solution as well as the optimality of your solution. So when a node is being removed, they are guarded by the tag, guarded by some of the tag vertices. So when there is no node left, everything is guarded, so the solution must be valid. And for optimality, we can do this by changing some other potentially better optimal solution into our solution. So we first say that for every leaf parent pairs that we considered in here, leaf nodes that are not being guarded. For every such pairs that we considered, the optimal solution must either include the leaf or the parent, because otherwise the leaf is not being guarded. And if the leaf node is in the optimal solution, we can replace it with its parents without affecting validity. Just say so say, for example, our optimal solution is this and this. We can transform it into taking the parent of the leaf vertex without affecting the validity, because the leaf is still guarded and that vertex is still guarded without so we are having another solution closer to our solution. And this is the proof sketch. This can be modified into a very formal proof, but you are not required to do that. So what if we also remove nodes that are being guarded? The proof will break, because for this part, S must either include the leaf or the parent. Otherwise, the leaf is not guarded. But this part no longer holds if we remove nodes that are being guarded. Because if we put a breakage at the removed guarded node, it can guard the leaf node. So and also we can actually turn this proof sketch into a formal proof by induction on the height of the tree. So we can tweak the algorithm a bit. So we only keep guarded nodes when they have unguarded children. So and we will not need to check this condition. We will not need to check this condition explicitly. We don't have to check which are guarded and which are not. If we only keep guarded nodes when they have unguarded children. So do you have any question regarding this midterm question? Okay, so we continue. So there are some other issues we found. For example, you should show that invariants still hold after when you update the data structure. For example, here the student said that this CI parent thing keeps track of the distance between I and parent. But when they call the change operation, it updates it only perform one update. So it updates this. Now when you consider a tree, so say this is I and this is J. I should. So if this is U, this is V, this is U, this is say I. So the problem is that this I to V is not updated. So the distance from I to V is not updated. So the invariance no longer holds. And if you don't prove that this invariance, you can somehow fix the invariance, you cannot use this thing after an update. Yeah, so it is crucial for you to show invariance still being held. And there are some other very common issues. For example, some of you abuse expected runtime when there's nothing random. You say that usually it is linear time or something like that, but we are nearly always talking about worst case running time. So you cannot use expected runtime unless we explicitly told you can use something random or your algorithm is using some random source or something like that. And some of you abuse amortized runtime. For example, they're saying that on in the sequence of operation, the total running time is O(n), not n. And then, but somehow later jump to the conclusion that the amortized running time is O log n over n or something. They're like, they are not even wrong. So it is if you want to use amortized runtime, please make sure that you understand what amortization means. It is worst case. It is still a worst case runtime, but it is. But you can have like multiple operations, and you take the average over those operations. So this is still worst case. It doesn't mean that when you use amortized runtime, you can just say that, oh, we assume that usually things will not that bad. It is not the. It is not giving. You need to prove that the average really holds, and also it is common for you to have induction that miss some certain cases. For example, the student defined this function up uki, and they are proving that the induction case is this. So actually, the I can be ignored here because it is just bound, some upper bound. But the main problem here is that both the U and K parameter are changing, and the induction here is only working on the parameter K. So you miss the parameter U. And typically try to spell out the entire induction hypothesis. It can generally help you to spot any problems in your proof. And then, so we have some additional hints for homework 2 and homework 3 in case you haven't yet figured them out in your resolution. So this homework 2 exercise 1, we typically use that sweep line method. So it is like you can split it into, you can only limit it into consider this region, and then use another segment tree or something like this to consider a sub-region of this red region. And for exercise 2, question 1, it is about the expected runtime of the expected height of the binary tree or something. You can try to count the number of ancestors. Yeah, count the expected number of the ancestor. So this is like in which cases can XB or can X be an ancestor of Y, etc. Then use this to compute the expected number. Like you define some indicator random variable and then try to sum them together. In the homework 3, for exercise 1, you can try to find the best friend efficiency using some sort of a prefix tree or something. And then after finding that, you can quickly check if they are best friend forever. And for exercise 2, many of you don't know that n log n is still quasi-linear. Quasi-linear means that it is ON1 plus epsilon for all epsilon larger than 0. This is quasi-linear, and n log kn is still quasi-linear. And you should try to prove this. This is a very simple proof. And you can use either central decomposition, heavy light decomposition, or Euler for exercise 2. It is quite simple. And also you can, for exercise 1, it is like asking you for ON 1.75 times solution. You can try to use the square root decomposition. But if you just solve question 2 and then say that something with this runtime still falls within this, it is fine. You will still get the full mark. Okay, so do you have any other questions? Or let me know if you want to have a more in-depth discussion about some of the questions. Homework to exercise 1.2. Okay. Oh, and also something I forgot to mention. If you don't know how to solve a certain exercise, try to give us a brute force but correct algorithm. If you give us nothing, we cannot allow you to resubmit because you didn't show any effort. But if you say you give us something not optimal, but it is kind of correct, we can still guide you to in your resubmission. And also, if you use something that is mentioned in the lecture, say it is a heavy light decomposition, you don't have to tell us how to compute that heavy light decomposition. Yeah. Okay. Now I'll elaborate on homework 2, exercise 1.2. Let me check what is the question. The nice square. So I'll just give you the direction for solving that. So you can try to use the sweep line method I mentioned. So at any time, you can say if you have a segment tree, it will only contain vertices with x between A and B. Or A and A plus K. So you want this margin to be k. And then from this, your segment tree can actually compute a certain maximal. Like when you add a point, it can span a region, and then you will add that point into the segment tree, and then you get the maximic segment tree. Because each point is contributing to you do addition over a range, say y minus k over 2, y plus k over 2. Add 1 to everything inside that range or something. Like, I am not super sure about this, but this is the rough idea. Like, I forgot if the constant is this, but this is the rough idea. Yeah, so is it clear? How this connects to the problem? Say, so you want to find how many points are inside a certain square with length k, and this point can contribute to like any square within any square with a center. How should I say this? You can consider it as the point is itself a square, and you want to find the number of you want to find the maximum number of overlapping squares centered at each point. Like, yeah, so for example, this is like overlapping 3 squares, and then the segment tree plus sweep line algorithm allows you to do that efficiently. Is this fine? How can we remove the points and update? Let's see. Oh, and remove the points and update this. Oh, you just do a range update. Like for each point it contributes this, and when you remove the point, you just do the opposite. Yes, the segment you just have one segment tree, And when you move this range, you're updating the segment tree, and the line doesn't move by one each time. Like you have a number of points, and you also have for each point you duplicate them into x minus k over 2 as well as x plus k over 2. Whenever you encounter this point, whenever you encounter something like this, you do this addition, and when you encounter this, you do this subtraction, and you sort them in the x-axis, and then you just move the line to every such coordinate.